Welcome to Brain Vision.
So in this question, we are given a stainless steel cylinder, right? So we have a stainless steel cylinder, and the stainless steel cylinder has an inner diameter of 4 inches, right? And wall thickness is equal to zero point 0.1 inch. Right now, if it is subjected to internal pressure of 80 psi and an axial load of 500 pounds, right? And the torque of 70 pound per feet. So what we need to do is that we are required to determine that whether yielding occurs or not according whether let me write it whether yielding occurs or not according to maximum distortion energy theory, right? According to maximum distortion energy theory. So let's start with the solution. Solution for this question is very simple, right? It's a little bit lengthy, but it's very simple. Now, first of all, what we are going to do is that we are going to start the solution by finding the stresses, right? The stresses, um, the internal pressure P grades, right? So to do so, we have to use chapter 8 theory. Now, chapter 8 theory tells us however, it only applies for thin walled vessels that have a ratio of radius and wall thickness of at least 10 inches, right? And in our case, it would be the ratio would be to T, it would be equal to 2 divided by zero point 0.1. That is 20, and 20 is greater than 10, right? So it means that we can use chapter 8 theory. Um, that is for thin walled vessels, right? So what we are going to do over here is that we are going to use equation 8.1 and 8.2, right? Because it only applies here since we have a cylindrical thin wall pressure vessel. So sigma sub 1 is equal to P times R divided by T. So that is 80 times 2 divided by zero point 0.1. That is equal to 1600 KSI. Right. Next, what we are going to do is that we need to find out the second principal stress, right? So that is equal to P times R divided by 2 times T. So that is 80 times 2 divided by 2 times zero point 0.1, and that is equal to 800 KSI. Now it is important to note over here that the above are not principal stresses, right? These are not principal stresses in this case, but it is how equation 8.1 and 8.2 are written. So we'll use the same annotation, right? And next we need to find out the normal stress created by the normal stress created by the axial force, right? So the inner radius of the circle, it would be r naught negative t, so that would be t 2 negative zero point 0.1, and that would be 1.9 inch, right? So the normal stress would be equal to F divided by A. Now F remains the same, and area, for area we are going to plug in the values. So R naught square negative Ri square, that is equal to 500 divided by pi times 2 square negative 1.919 square, right? So calculate it and we'll get that the normal stress, right, that is caused by the force exerting on it is equal to 4.408.1 KSI. Now we found in problem 10.59 that the distortion energy theory can be written in terms of um, it can be written in terms of sigma sub x, sigma sub y, and tau xy, right? So that equation is sigma sub y square is equal to sigma sub x square negative the product of sigma sub x, sigma sub y plus the square of sigma sub y square plus 3 times tau sub xy square, right? So now finally we have a torque T that creates a um, shear stress, right? Tau that creates a shear stress. So chapter 5 deals with torsion, right? Recall your um, previous knowledge of chapter number 5, right? So chapter number 5, it um, deals with torsion, and from chapter number 5 we would be using equation 5.6, and this equation gives us tau is equal to T times R naught divided by J, right? And that is equals to pi by 2 into R naught raised to power 4 negative R sub I raised to power 4, right? Parenthesis close. Now what we're going to do over here is that simply we are going to plug in the values. So tau is equal to 2 times 70 times 12 times 2 divided by pi 2 raised to power 4 negative 1.9 raised to power 4, right? So just calculate it and we get that it is equal to 360.4 KSI, right? So now from here what we are going to do is that we are going to figure out the direction of these stresses, right? So looking at the directions of sigma sub 1 and sigma sub 2 from chapter 8, again these are not principal stresses, they are just stresses, but we are using the same annotation as in chapter number 8, right? So we see that sigma sub 1 is in the y direction, right? And sigma sub 2 is in the x direction, right? Now let's recap that sigma sub x is equal to sigma sub 2 plus sigma sub fx, right? That is equal to 800 plus 408.1, right? That is equal to 1208.1 KSI, right? And sigma sub y is equal to sigma sub 1, that is equal to 1600 KSI, right? And the tau is equal to 360.4 KSI that we just calculated above. Right now again in problem 10.59 We found that the distortion theory, it can be written in terms of sigma x, sigma y, and tau xy, right? So we are going to use this equation, that is sigma sub y square is equal to sigma sub x square negative times sigma sub x sigma sub y plus sigma sub y square plus 3 times sigma sub tor sub x y square, right? Just plug in the values and we'll get that sigma sub y is equal to 1.5736 into 10 raised to power 3 psi, and that is approximately equal to 1.57 psi, right? Now look at page number 882, right? Page number 882, and we see that the yield stress for our material is equal to 30 ksi, right? So as you can see over here, that 1.57, right, it is less than 30, right? So it means that the material does not yield, or it does not fail according to the maximum um, distortion theory. And this concludes our answer.